All right, so we're going to look at some of the 2.4 homework. So this was when we were talking about left and right side limits. So in this first question, it just says use the function and its graph to answer the questions. We could have graphed this ourselves. Remember, one of the keys for graphing a piecewise is to just kind of plug in, sorry about that, to plug in the breakup value just so you can see. So we know that we're going to have the point 3, 3 with circle, and then plug in this guy. So 3 plus 1 is 4. So we're going to have 3, 4 also with an open circle. So you see those 2 points labeled with open circles. And then as you move left, you have a slope of -1. So you can rise 1 and go left, rise 1, go left. So that's that one. And then for this one, you have a slope of +1. So up, over, up, over, up, over, and that's that guy. So we could have graphed this ourselves. So now we can answer these questions. So the first one says, okay, as I approach from the right, what's going on? So as you approach from the right side, that would be, well, that where that red arrow is. So you're coming in from the right, and you're going to that open circle right there. And where is that at? That's at 4. Now, as you're coming in from the left, that's this one, you're getting super close to that open circle, which we know is at 3. So coming in from the left, the function's going to 3. Coming in from the right, the function's going to 4. All right, so then part B says, so does the limit in general exist? And the answer would be no, they didn't agree with each other. So one was 4 and one was 3. So I would go with A there. So you can have a piecewise function. They have to agree at that breakup point. So if they agree, then you're good to go with a piecewise. But otherwise, if there's a break there, you have a problem. So remember, we had a theorem that said that a limit exists if and only if its left limit exists, its right limit exists, and those are equal to each other. So we would go with A doesn't exist because the left and right are not equal. All right, and so then C is asking about 5 up in that graph. So let's go back to this graph and check out the number 5. So here's 5. So as I approach 5 from the right, I'm going to 6. And as I approach 5 from the left, I'm also going to 6. So coming in from the left, you're going to 6. Coming in from the right, you're going to 6. So that means that the limit in general is the two-sided limit will also be 6. So where was that at? Yep, so we're just going to go with 6 for both of these. So coming in from the right, it was 6. Coming in from the left, it was 6. And then we would say, yes, the limit exists and it's equal to 6. There's the answers right there. Where's the next question? Okay. There's only one question on the test. Oh, that was very strange. Okay. So question number 2 is exactly the same. So notice that this one is a little bit different, but watch this. The breakup point is 3. If you put 3 into the top one, you get a 1, which means you have the point 3, 1 open. If you put a 3 into this one, well, you get a 2. So put in a 3, you get a 2. This is closed because it was equal to 3 there. And then if you put a 3 into this one, you get 1. So this is the point 3, 1 open. So even without graphing, notice that you get the same value coming in from the left or the right. So this first one would be coming in from the left, because see, it's less than 3. This would be coming in from the right, because it's greater than 3. So coming in from the left, you get the number 1. Coming in from the right, you get the number 1. Therefore, the limit exists, and it is 1. Okay? The fact that it's defined to be 2, you have a closed circle at 2, that's its definition. That's not what the limit is. Remember, the limit is what happens when you get really close. So I'm going to just skip the rest of that one. You guys got that? All right, so let's look at question number 3. So this graph is a little bit different. It's another piecewise, though. So we're going to do the same thing when it comes to -1. Do notice that that second piecewise function is undefined at -1 because of its denominator there. So we're not going to be able to actually plug in a -1 to that one like we'd like to. But from the top one, if you plugged in a -1, you'd get a 0, and there's going to be a closed circle there. Here, we can't actually plug in the -1. And if you look at the graph, that dotted line means that as it gets close to negative, jumps and jumps and jumps and jumps, up and down, up and down, up and down. So it's not going anywhere, you guys. There's no way to kind of pinpoint it. Now, coming in from the left, you're good to go. You're at 0, right? So coming in from the left, it's going to be at 0. Coming in from the right, it doesn't exist because it oscillates. It never settles on a value. Okay, so this first one is asking from the right, so this is undefined or doesn't exist. Oh, that was it. That one said yes. So let's not choose that as our answer. So let's see what these answer choices are. So no, because there is no real number to which the function's values stay increasingly close as x approaches -1 from, I'm guessing that was from the right, and it just got cut off. So we're going to go with B on that one. I can't actually select it, but it's not getting close to anything. It's just jumping all over the place. Now, as you come into -1 from the left, it's 0, right? If you look at the y value there is 0. So that is yes, and it's 0. C says, so does the limit exist in general? And you would say no. The right-hand limit doesn't even exist, so they're definitely not equal to each other. So we'll go with B there. No, because the left and right aren't equal. So remember, you have to be equal from the left and right. So here's the answers. No, because it's not getting anywhere. From the left, it's 0, and no, because they're not equal. All right, so let's look at number 4. And here what we want to do is try to find the limit as x is approaching 5 from the right of this function. So let's look at where there might be problems with this function. And it does have denominators. So let's just, without even thinking about the 5, let's just look at this. We know that x plus 1 can't be 0. So in other words, x can't be -1. We also know that x squared plus x can't be 0. So if you factor the x out of that, that tells you that this can't be 0. So x can't be 0 or -1 again. So we do have a domain problem here. The domain here is -infinity to -1. And then we can go from -1 to 0. And then we can go from 0 to infinity. So notice where these trouble spots are would be -1 and 0. So if we were approaching either of those places, we'd have to do a little bit of thinking, but we're just approaching 5. Let's just plug it in. So if I just plug in the 5, even a -5 to make things complicated. All right, so we're going to get 30 over 6 times, what's that, 45 over 30. So then the 30s divide out. 3 goes into 6 twice, 3 goes into 15, oops, 3 goes into 45 15 times, so we end up with 15 halves. Okay, so we weren't approaching a trouble spot, so rational functions are continuous everywhere, except where their denominators are 0. So we only have a problem there where the denominator is 0. All right, so let's look at number 5. This one looks like a big mess. So we're approaching 0 from the right-hand side. Notice here that h is actually not allowed to be 0 because of the h in the denominator, but also h squared plus 10h plus 17 has to be greater than or equal to 0 because it's under a square root. That doesn't factor nicely, so let's hope that we don't have to deal with that situation. But notice what happens if we try to plug the 0 in. If we try to plug in h equals 0, we're going to get 0 plus 17 minus the square root of 17 divided by 0. So in other words, we do get 0 over 0. And whenever you get 0 over 0, that's kind of your hint that something's going on here. So we can try to manipulate this and get an answer. So let's play with this. Now I see the square root, so I'm thinking let's do conjugates. So remember, whenever you multiply a binomial expression by its conjugate, the outer and inner disappear from foiling, and then you get to square the first one and square the last one. So see, when you square a square root, there's no more square root. So that's why we really like multiplying by conjugates. So let's check this out. I'm just going to multiply it from here and pretend like that's my fraction line. So I'm going to multiply by the square root of h squared plus 10h plus 17 plus the square root of 17 over, same thing. We're just multiplying by 1 here. It's just a special 1. Okay. We're going to multiply by that, and that part I just erased told you how the top's going to end up looking like. It's going to be the first one squared, which would just give you h squared plus 10h plus 17, minus the second one squared, which would be 17. You see, this is that a squared minus b squared. On the bottom, I'm not going to mess with this. I'm just going to leave it. All right, and now notice on top, you have 17 minus 17. So those are actually, those cancel out. They're gone. But also notice I can factor an h out of that piece. So let's see what that's going to look like. So I can factor an h out. It would leave me with h plus 10. And then divided by h times h squared plus 10h plus 17 plus the square root of 17. So we got this big old denominator. So now what we can do is divide out those h's, and we should be able to now plug that 0 back in. So let's check out plugging in that 0 now. On the top, we'd get 0 plus 10. On the bottom, we would get the square root of 0 plus 0 plus 17 plus the square root of 17, which gives me 10 over 2 square roots of 17, which is really 5 over the square root of 17. So beautiful. And you can rationalize that if you choose. If you rationalize, you're just multiplying top and bottom by that root. So you get 5 square root of 17 over 17. That's an equals. So either of those is fine. Either leave it this way or you can rationalize it. But looks good. So just watch that. Notice it didn't matter that we were coming from the right in this case, but sometimes it does matter, like in the next one. So let's look here at number 6. So number 6, did I just lose the function? No. We have an absolute value in number 6. So absolute values, by the way, are actually piecewise functions. They look like this. So the absolute value of x is equal to x if x is greater than or equal to 0, and the opposite of x if x is less than 0. So see, if the thing inside is negative, what you're actually doing is taking the opposite of it. If the thing inside the absolute value is positive or 0, just dropping the absolute values. So let's check this one out and kind of see what's going on. So notice that the denominator is x plus 9, so we're not allowed to plug in the -9 per se. If we tried, we would get 0 over 0. So I'll just point that out. So if you plug in, you are going to get 0 over 0, which means we're going to mess with this thing. So let's consider that absolute value. What's going on with this? When x is approaching -9 from the right-hand side, okay, which means you're plugging in something a little bigger than -9. So you could even, just kind of, oh, not supposed to say, you could even play with it and do something like -8.9. You see, we're coming into, think about your number line. Here's your -9. If you're coming in from the right-hand side, then you're picking something a little bigger, which would be something like -8.9. So if we were to plug that in, what would happen here? -8.9 plus 9. You see how we'd get a positive in there? Which means I'm allowed to just drop that absolute value. So see, we're following this one because we have a positive number in there. So we're allowed to just drop it. So let's look at that first one again down here. So the limit as we approach from the right is going to be x plus 11. Now, notice I'm just getting rid of the absolute value. I can just drop it because I know what's inside is going to be positive. So now those divide out. I get x plus 11, and I can plug the -9 into that. So that's going to give you a 2. All right, so now let's see what happens if I plug in coming in from the left. So if I plug in coming, all right, so let's look at this as x is going to -9 from the left. And think about that number line again down here. If you come in from the left, you're going to get something like, I don't know, -9.1. You see a little bit less than -9. So if you plug in, say, a -9.1, you are going to get a negative under here. Okay, so what do you do if you get a negative inside your absolute value? You use this, which means you take the opposite of whatever's inside. So looking at this one, we're actually going to have x plus 11, and we're going to have the opposite of x plus 9. So see, we can still divide those out, except that there's this -1 hanging out. You see that? So this is actually negative x minus 11. If he gets distributed through, that's a -1 there. So when I plug a -9 into that, it's positive 9 minus 11, which is -2. So coming in from the right-hand side, we're going to get a 2. Coming in from the left-hand side, we're going to get a -2. And, oh, there's the answers kind of sitting there. So remember what this means, because they don't agree with each other. If this asked just for the limit in general, we would have to say that it doesn't exist because they don't agree with each other. All right, and let's look at one more, because these are all doing the same thing. I have a lot of these. They're fun. Okay, so let's look at, I don't know which one. This one's really not that exciting. Let's try this one. Okay, so the idea is we know that the limit as theta approaches 0 is sine theta over theta is equal to 1. Notice then if you were finding the limit as theta approaches 0, theta over sine theta, so let's say it was reversed, this is the same thing as the limit as theta approaches 0 of 1 over sine theta over theta. You see, oh, that wasn't a theta. I tried to do that too quick. Okay. So you see how these are the same thing, dividing by a fraction, you would flip it and it would look like that guy. And then from our limit laws, we know that we're allowed to break this up. So the top here is 1 because it's a constant, and then the bottom is 1 by the theorem, so we end up with 1. So that's kind of the little proof that it really doesn't matter which way the fraction is, you're still going to get 1. So even though the theorem is written this way, it's also true that the limit as theta approaches 0 of theta over sine theta is also 1. So just keep that in mind. All right, so the idea then is to try to get, so things are the ones that cause problems because the sine of 0 is 0. So see, if we just tried to plug a 0 into this one, let's see what would happen. Always try plugging it in first. If I plugged a 0 in, I'd get 0 plus 0 over 8 times the sine of 0 is 0, cosine of 0 is 1. So notice that is 0 over 0. So we get the 0 over 0. We know that there's something we can do to manipulate this. So we're going to play with it. And what we're going to do is try to get these sine theta over thetas, these kind of matching places. Now first, do notice that the top factors, so I'm just going to factor a 7x out of the top. That leaves me with 1 plus cosine 7x. And then on the bottom, we have an 8, a sine 7x, and a cosine 7x. So our main problem here is this sine 7x. What I'm going to do is I'm just going to kind of extend this. And, oh, we don't even need to. Check this out. There's already a match here. You see how it's the sine of 7x, which matches with that 7x. You guys probably can't really see that highlighting. So these match. So according to the theorem, the limit for that piece is 1. If they hadn't matched, so what I was about to do is I was going to like tack on a 7x here. I just would have had to put it on the top and the bottom to get that match. But the 7x was already there. So kind of sweet. All right, so now we just kind of separate that out and say, okay, so we've got this 7x over sine 7x. And then left over, we would have a 1 plus cosine 7x over 8 times the cosine of 7x. So the limit for this part, this one goes to 1, which is kind of nice. And then for this next part, we can just plug the 0 back in. So 1 plus the cosine of 0 over 8 times the cosine of 0. And the cosine of 0 is 1, so this is 1 plus 1 over 8, which is 2/8, which is 1/4. So pretty cool. Let's do one more for the heck of it. How about, I don't know, look at this last one here. So for this one, first off, this has tangent and cotangents in it. We kind of like things to be sine and cosine. So before I do anything, I'm just going to rewrite this with sine and cosine. So this is sine theta over cosine theta divided by theta squared. Cotangent is cosine. Is that 22 theta? I guess so. Divided by sine, 22 theta. So this is kind of a big mess. Let's flip that bottom guy up. So we've got sine theta over cosine theta. If we flip that, the sine will end up here. So here's the 22 theta. Cosine will end up on the bottom. So there's the cosine of 22 theta. And then we've got theta squared. He was already down there. I guess I should have put him before, but what if I put him over here? And I'm going to write that as theta times theta, because I'm thinking I'm going to need to. All right, so it looks like this. Notice if we plugged in the 0 right now, the top would definitely be 0, and the bottom would definitely be 0. So we do get 0 over 0. We know we can play with this thing. So what we got to try to do is kind of match these things up. So if you look at this first side, he has a theta, so we need a theta to match with him. Oh, there's one. So we can put those two together. But now look at this next one. This next one has a 22 theta. Can't see that highlighter at all. Let's make it a little darker. Has a 22 theta. Oh, but I only have a theta down at the bottom. It needs to be a 22 theta. So let's just put a 22 on top and a 22 on the bottom. That makes it a 1, right? And then there's a 22 theta. That wasn't a very good highlighter there. Oh, that just made it worse. Anyway, there's a 22 theta to go along with him. So now I can rewrite this and match people up. So sine theta over theta times, we've got a sine 22 theta over 22 theta times, let's write down what would be left over. So there's a 22 on top. On the bottom, there's a cosine theta and a cosine 22 theta. All right, so that accounted for everyone, right? We got this, this, and this. Check. We got this and this and this and this. All right, we got everybody. This one goes to 1. This one goes to 1. And then over here, we have 22 over cosine 0 times cosine 0, just plugging in the 0, which gives me 22 over 1, which is 22. So pretty cool. All right, so that is the end of 2.4 homework. Again, there's just some more of those. The ones that we kind of skipped, they're just the same kind of problems. You're just going to kind of manipulate it and try to get this kind of matchup. So if you have a sine 3 theta, you need a 3 theta either below him or above him, depending on where he's at. So again, don't forget, you can also do this, right? This will also get you a 1. So, all right, that's it. Dun, dun, dun.